Hey everyone, welcome back again. So in our today's interaction, we are going to start with an interesting topic as well as the important part of electromagnetic induction. So today, we are not going to talk about the complete electromagnetic induction, but we are going to take up the important as well as that part from which the majority of tricky questions come in physics. Alright, that part is Lenz law. So, first of all, let us see that where the role of Lenz law comes into the picture, and gradually by taking a lot of examples starting from the zero up to the best, we will try to cover each and every aspect, each and every type of problems which have already come in Neet or which are probable to come in the Neet for the upcoming year. Alright. So, as we know that the induced EMF is given by minus of d phi m by dt. This is the fundamental formula and this is the only formula around which the entire story of electromagnetic induction keeps going. Alright. So here you talk about the induced EMF, here you talk about d phi m by dt means the time rate of change of total magnetic flux, and the role of Lenz law is explained by this negative sign, or I should say this negative sign is as per Lenz law. Now what is this Lenz law? Basically this is nothing but the contribution, or you can say the energy aspect, the conservation of energy aspect in the electromagnetic induction. So it is based on conservation of energy. That it seems that if you will keep changing the magnetic flux, linked with a coil, the electromagnetic induction will happen, or you can say the EMF will be induced in that particular coil. And if we are talking about the closed loops, closed coils, then definitely because of an induced EMF, there will be an induced current. Alright. So Lenz law basically told you regarding the direction or polarity of induced EMF as well as induced current if it flows. So according to Lenz law, the direction of induced current, direction of induced EMF or current will be in such a way, that it always tries to maintain the magnetic flux. In the entire unit of electromagnetic induction, your preference is to always the maintenance of the flux. You don't want to change the flux. If flux is increasing, then induced EMF or current will be such that it will try to reduce the enhanced value or increased value so that the flux will be again maintained. And if the flux is decreasing, again the induced EMF or current will try to increase it. So direction of induced EMF or current will be such that it always opposes the change of magnetic flux. It always opposes the change of magnetic flux which is responsible for its production. I'll repeat my words. If there is no change in the magnetic flux, then there will be no induction, no EMI, no electromagnetic induction. But if the magnetic flux will keep on changing, definitely the EMF will start getting induced. And if the loop is closed, definitely there will be an induced current. So whichever EMF or whichever current has been induced, the direction or polarity of that induced EMF or current will be such that it will be always opposing its production reason. It will be always try to oppose the change of magnetic flux responsible for its production. Means if the incrementing magnetic flux, if the incremental change of magnetic flux is responsible for inducing an EMF, then the induced EMF will try to decrease it. And if it is a decreasing change which is responsible for the production of EMF or for the induction of EMF or for the variation of magnetic flux, then we will say the induced EMF or induced current will be in such a way that it will try to increase. Once again, if there is no change of EMF, if there is no change in magnetic flux, there will be no induction of EMF. Okay. If the magnetic flux is increasing with time, the EMI will happen and the induced EMF will try to decrease this flux. And if the magnetic flux is decreasing with time, then in that case current induced or EMF will be induced in such a way that it will try to increase. So the thing is that always prefers to oppose the change. The induced EMF or induced current always prefers to oppose the change responsible for the production of EMF or current. Alright, we will see some examples. So basically with examples today we will try to have a good command on this topic of Lenz law, and moreover the notes and everything will be attached in the description of the video. And for these type of concept booster videos, make sure that you subscribe the channel and you regularly watch the important content and the notifications which is shared by the team. All right, so let us talk about the first example. Example 1. I will say that suppose there is a region of magnetic field or magnetic field strength B0, the constant magnetic field strength is there and it is minus K cap. So if it's a constant magnetic field, electromagnetic induction will happen, and minus K cap means away from us. So I am showing it by a cross. Cross means inwards, alright. And suppose there is a coil. I am starting with the basic NCERT example. Suppose there is a coil and this coil you are entering, you are taking this coil inside the magnetic field region and you are asking the direction of induced current. Another one, let us suppose we are having this coil, circular coil, and you are taking this out of the field. And again your question is that determine the direction of induced current. Another one is that suppose it's a square frame, it was already in the magnetic field region, and you are trying to move it like this. So these arrows are representing the direction of velocity vector, alright, where we are moving it. So suppose we are moving this coil with this velocity vector inwards. Then what will happen to this coil? You will say in this coil the magnetic flux, the inward magnetic flux keeps on increasing. If the inward magnetic flux keeps on increasing, the loop is closed and the conducting one. So you will say induced current will try to reduce it. I repeat, if the increase in the flux is responsible for the induction, then the induced current will try to reduce it. If decrease in the flux is responsible for the induction, then the induced current will try to enhance it. Okay, change is always opposed. Incremental change is there, so decrease it. Decremental change is there, so increase it. Alright, so inward magnetic flux keeps on increasing. There will be an induced EMF, there will be an induced current that will try to reduce it. That is inward, or you can say cross magnetic field if you want to reduce, which means outwards dot field must be, dot magnetic flux must be produced. If you try to produce the outward magnetic flux, then by right hand thumb rule, if it's a clockwise current, then the thumb is pointing inwards. If it's an anti-clockwise current, the thumb is pointing outwards. So you will say this implies anti-clockwise current, counterclockwise current, anti-clockwise current must be induced. Understood? So what we can comment about is that if it is all about this first loop, in this first loop, the direction of induced current must be anti-clockwise. Anti-clockwise means it should be moving like this. This is the direction of induced current. All right. Let us talk about this one, circular loop which is being taken outside, the magnetic field strength. So here what we'll say for this loop, we will say with time, this loop is coming outside the field. So you will say with time, cross magnetic field or magnetic flux decreases. If this cross magnetic flux decreases, induced current will try to increase it. Means this implies we need some cross magnetic flux. See, the cross magnetic flux was linked, but if you keep on taking it out of the field region, the cross linked magnetic field or flux will keep on decreasing. And if the flux is decreasing, EMF will induce, sir. Loop is closed, so current will induce, sir. But this induced current will be responsible to oppose the change for which was the reason for its production. So decrease in the magnetic flux was responsible to produce the current. So the produced current or the induced current, which will it will try to oppose the change. Means if decrease is the reason, it will try to increase it, which means we need cross magnetic flux. And from the right hand thumb rule, if we need the cross magnetic flux, the current direction must be clockwise. This implies clockwise induced current. Understood? Slowly we will start taking the much complicated examples also. It will give you some more clarity. But as of now, I would just say that these are the illustrations which are purely from the NCERT background. Let us talk about this one, third loop. It's a square loop. B vector is equal to B naught minus K cap. B vector is equal to B naught minus K cap means that's a uniform magnetic field region. Right? So in that case, the green colored loop, this first loop was entering into the region. This loop was exiting from the region. But if you talk about this particular loop is already, this square kind of loop is already inside the uniform magnetic field, and you will keep moving inside the uniform magnetic field only. So you will say with time here for this loop, with time it was already completely inside the region and it is traveling inside the uniform field region only. There is no change in magnetic flux, and if there is no change in magnetic flux, this implies no EMI, no electromagnetic induction. No electromagnetic induction will happen, no EMF induced and no current induced. And if there is nothing much, I mean this phi m value here, it has become constant. If it has become constant, constant's derivative is 0, there is no induction and hence no Lenz law will come into the picture. Alright. So sometimes if the examiner is asking you that as per Lenz law determine the direction of induced current, you also notice that the answer could be that sir there is no induced current, because if there is no variation in the value of magnetic flux linked with the coil, there is no electromagnetic induction. I hope the logic is clear to you. So first thing is, primary condition is whenever there is a magnetic flux linked with the coil, that changes with time, an EMF will be induced in the coil. And if the coil is closed, if it's a closed loop, then there will be a current induced in the coil. The current so induced and the EMF so induced will be inducing in such a way, with such a direction, with such a polarity that they are responsible to oppose the change. They will always try to oppose the change, which was a reason for their creation, which was a reason for their induction. Alright, so that's what we have written over there. The direction of induced EMF or current will be such that it always opposes the change of magnetic flux. It always, I am not saying it always opposes the magnetic flux. No, it always opposes the change of magnetic flux. Means if magnetic flux keeps on increasing with time, keeps on getting stronger, you will try to make it weaker. See, you want to reduce it. And with time, if the magnetic flux linked will keep on getting weaker, then your tendency will be, you will try to make it stronger. You will try to strengthen it. So if the magnetic flux doesn't change, no induction. If the flux keeps on getting stronger, you will try to make it weak, may oppose it. If the flux keeps on reducing, keeps on getting weaker, you will try to strengthen it, you will try to support it. Alright, understood? Chaliye. So this was the first example. If you want, you can take the screenshot, then I'll take you ahead. Alright, I hope you have taken the screenshot, and make sure you keep on revising them. Once you have the screenshots, I will try to assure this that whatever we are learning today in this small session, out of these, one of the examples similar to it or exactly same, we will try to have it in the final Neet exam. Alright, so let's continue our discussion with the same hope. Example 2. Again, the thing is that we have to tell the direction of induced current. Suppose B vector is equal to B naught T and it is K cap. B naught T K cap. So K cap means it's a dot field. It's a dot field which is constant with space or uniform with space but varies with time. You see, it's not varying with the position or with location. So you will say same or uniform throughout, but varies with time. So it is a time varying field, varies with time, and in short form we call this as, that is, TVMF, time varying magnetic field. What do we call it? TVMF, time varying magnetic field. And suppose in this magnetic field there is a loop, arbitrary, randomly shaped loop, it's a closed loop, right? The question is again the same, sir. Determine the direction of induced current. So how to judge that? You will say here, with time t, time will always keep on going, right? Time can never reduce, time will always keep on increasing. So with the increasing time, you will realize that this magnetic field is directly proportional to the time. So with time, the magnetic field increases. The outward magnetic field, dot means outwards or K cap means towards us. So outward magnetic field increases. If outward magnetic field increases, this implies the outward magnetic flux increases. So there will be an EMF induced, and since the loop is closed, there will be a current induced. So here induced current will always have a tendency to oppose the change, oppose the increment ko if you want to oppose, oppose the increasing, if you want to oppose the stronger, make it weaker, means give opposite. Induced current will try to oppose the increment, that is, will try to reduce outward flux. If it will try to reduce outward flux, this implies we need to introduce inward flux. For first few examples, I am writing it in terms of language. We need to introduce inward flux. So this implies the induced current will be in such a way that outward incremental flux will be opposed. So we need the inward, and by right hand thumb rule, if we need the inwards, the current, the fingers must be curling in the clockwise sense, the current must be flowing in the clockwise. So clockwise current is required, which means here I will say the current induced will be in such a way. This will be the induced current. Understood? This will be the induced current. Let us see one more time. I am talking about example 3. In this example 3, you will say B vector will be equal to B naught by 2 plus T, and it is K cap only. Okay, K cap only. This is some expression of magnetic field. Here if you notice what is so special regarding this magnetic field, you will find that with time, the strength of magnetic field, B magnitude, because denominator will keep on increasing, so overall fraction will keep on decreasing. The strength will decrease. Again, it is the case of TVMF, time varying magnetic field. So in time varying magnetic field, again you have got one illustration in which with time, again it's a K cap here, again it's a K cap. So if you have this K cap, again that's a dot, and see I am drawing uniform field equispaced marking, because it doesn't vary with space, it varies with time. It is not varying with space, it is varying with time. So this is a loop that can be any random shaped loop. This time suppose I am taking it a rectangular loop. It doesn't matter here, shape doesn't matter here. So you will say, what will be the analysis? You will say that if with time the magnetic field strength keeps on decreasing, this implies induced current will try to support the reducing outward flux. See, the flux linked was outward, there is no doubt in that. The flux linked is outward, and this outward flux is not constant with time, it keeps on decreasing with time. If the outward flux keeps on changing with time, there will be an electromagnetic induction, there will be an induced EMF, there will be an induced current, but this induced EMF and induced current will be in such a way that it will again be responsible to oppose the change which was in return creating it. So what you will say, that in the outward flux was showing a decremental change, because of which there will be an induced current, but this induced current will be responsible to oppose the decremental change, which means this time we want some increment, we want some support. This implies support the outward magnetic flux. And if you want to support the outward magnetic flux, then by right hand thumb rule, if we want the outward opposing flux, the current induced must be anti-clockwise. So you will say counterclockwise induced current, counterclockwise induced current, and hence this will be the direction of induced current. I hope the logic is clear to you. Alright. So in the first example, what we have learned, that magnetic field was not, this magnetic field, you can say, it is constant with respect to space. It is constant with respect to space or location, and it is constant with respect to time also. It is constant with respect to time. So the magnetic field was constant or variable, it doesn't matter a lot to us. What matters to us is that whether the magnetic flux linked with the coil changes or not. So here the magnetic field was totally constant, neither it was varying with space nor it was varying with time, but still sometimes you are entering a coil, sometimes you are taking out a coil, sometimes you are moving the coil within the region of magnetic field. So in all such different behaviors, the magnetic flux, how the magnetic flux linked with the coil changes, that also keeps showing different behavior. Sometimes it keeps on increasing, sometimes it keeps on decreasing, sometimes it doesn't change at all. And according to the Faraday's law of electromagnetic induction, this is Faraday's law of electromagnetic induction, that whenever the magnetic flux linked with the conducting coil changes, an EMF is induced in it. And according to Lenz's law, the direction or polarity of this EMF or induced current will be in such a way that it will always try to oppose the change of magnetic flux. Its tendency is to always the maintenance of the magnetic flux. If the magnetic flux keeps on increasing with time, the current will try to reduce it. If the magnetic flux keeps on reducing with time, the current will try to support it. If the magnetic flux doesn't change at all, the current will not be even induced. Similarly, and this was happening when the flux or field was not, the field was not varying. This time the magnetic field strength keeps on increasing with time. This time the magnetic field strength keeps on decreasing with time. Understood? So this is all about when you are moving the coil inside a given region of the magnetic field, depending upon the strength, depending upon the, depending upon its magnitude or expression, this, that. There are some more examples in which now the magnetic field will not be given, but the source of magnetic field will be given. Say it a bar magnet or say it a current carrying conductor. So let me take till example 3 we have discussed. Let me take another example, example 4. Suppose this is a current carrying conductor. It's a current flowing in it. It's a long conductor coming from infinity going to infinity. It's a long conductor and a current is flowing in it, which is a constant current. Okay, it's a constant current. So we know that the magnetic flux linked with it is, according to the right hand thumb rule, it will be a dot field here and it will be a cross field here. Because of this current carrying conductor, it will be a dot field here, it will be a cross field below it, and you will say here, as soon as you keep on going away from the conductor, the strength of the magnetic field B, which is cross here, that keeps on reducing. And similarly, if you keep on moving away here, the strength of magnetic field, which is a dot, that will also keep on reducing, which is very simple here. Near to a mass, the gravitational field will be stronger. Near to a charge, the electric field intensity will be stronger. Similarly, near to a bar magnet or a current carrying conductor, naturally the magnetic field strength is also stronger. But as soon as you keep on going away from it, you will realize that the strength of the magnetic field reduces. I have given you few loops. You need to tell me how the induced current will be obtained in that. How the induced current is obtained in that. This is the configuration given to you. This is the situation. Now loop 1, this is the loop 1, okay, this is the loop 1 in which you have to tell me the induced current. It is just moving towards the conductor. Loop 2, let me take this loop 2. Loop 2 is just placed here, placed at rest, not moving anywhere. Loop 3 is moved parallel. Loop 3 is moved parallel to the current carrying conductor. And loop 4, suppose I am talking about the loop 4, this loop 4 keeps on going away from the conductor. So loop 1 is moving towards the conductor, loop 2 is just placed at rest, loop 3 is moved parallel to the conductor, and loop 4 is moved away from the conductor. But the conductor's linked magnetic flux, the nature of the magnetic flux linked with the current carrying conductor is not the same on both sides. Upper side it's a dot, lower side it's a cross. As soon as you keep on moving away from the current carrying conductor, the strength of magnetic field will surely keep on decreasing. I hope that's clear for us. All right. Now let us talk about them one by one. Okay. So in loop 1, you will say that the loop is coming closer and closer to this current. So if this loop keeps on coming closer and closer, you will realize that the dot flux keeps on increasing. If the dot flux keeps on increasing, means you have to oppose it. If you want to oppose the dot, then you need a cross. If you want to oppose a dot, then you need a cross. If you need a cross, the direction of induced current is going to be clockwise. Okay, so clockwise will be the direction of induced current. Okay, let us talk about loop 2 and loop 3. You will realize that in loop 2, there is no change in magnetic flux. Although the magnetic flux is cross type, but there is no change in the magnetic flux with time, because current is not increasing or decreasing. The loop is not at all moving, neither it is coming towards stronger field nor it is going toward away from the field like that. So there is no change in the cross magnetic flux with time, and hence there will be no electromagnetic induction, no EMF induced, no current induced. What about the green colored, sir? It is also moving within the field, but there is no change in strength of linked magnetic flux. No change in the strength of linked magnetic flux. If there is no change, then definitely you will say this implies no electromagnetic induction. There is no EMI happening here also. And what about loop 4, sir? In loop 4, you are going away. If you are going away, the flux will be reduced. But which type of flux will be reduced? So you will say cross type of flux keeps on reducing. If cross type of flux keeps on reducing, this implies you have to support cross. If you have to support cross, again, the cross magnetic flux, the cross type of magnetic flux in this region keeps on reducing. You want to oppose the change. So if that's a decremental change, you want to support it. If you want a cross, this implies again the current will be clockwise current is induced. Understood? Clockwise current will be induced. So there are n number of cases here. If you will study regularly, you will realize that model by model, topic by topic, here we cover each and everything which is relevant and probable for the upcoming NEET exam. So right now in these lectures, we will try to emphasize on those topics in which majority of students, majority of aspirants like you are having a tendency to do some mistake. So we will try to emphasize on those mistakes and we will try to prevent those mistakes done by you. Okay. So let's try and let's maintain the pace. Let's try learning together. And every day, one thing which I tell to each of my students is, whenever you are doing something now, you should be doing it in a carefree manner. You need to understand the difference between carefree and careless. You need not to be careless, but you should be carefree a bit, because if you will poke yourself too much that, oh, this is a topic in which the mistakes are happening, mistakes should not happen, trust me here, there will be a high chance that there will be some mistake happening, because you are taking too much of the pressure. That much pressure, that much stress is not required. What is required is you do a lot of variety of problems in your practice time, in your preparation time, so that any common mistake which is having a tendency to occur, you will be able to prevent those mistakes, number one. And make sure that you revise every day whatever you are learning from morning to evening. Make sure you revise that before you sleep every night. So in this way, when you review all your efforts, whatever you have made in the day, in this way you will review all the errors also, whatever the mistakes you have done throughout the day. So if you review your mistakes, if you remember your mistakes, then the mistakes will not be repeated. And if you don't, you don't emphasize on what mistakes you have done, if you don't look at it carefully, if you don't review your mistakes, then there is a high chance that you might be repeating your mistakes. So try and understand. Number one, on everyday basis, you have to learn some crucial topics. You have to learn thoroughly the relevant content in the NEET. Number two, whatever you are learning throughout the day, you have to put that in practice also. You have to attempt some related problems. Number three, whatever problems you are attempting, whatever mistakes you have done, whatever new content you have learned from morning to evening, make sure before you sleep every night, you must revise it. And for further any kind of assistance, support, and the deadlines and notifications, everything, you can stay connected to the channel. You will get the notifications whenever a new lecture is uploaded on the channel, and any new content, any new notification is there, we will keep updating it. Okay, so stay connected here, and all the best, and stay smiling while you prepare. Let's hope for a good preparation as well as a good performance. All the best.